Hello again, and welcome to week 3 of your online organic lab for this semester. Today we're going to be discussing crystallization in terms of reading material in your textbooks, if y'all have them. Section 8.2, pages 89 through 97. This will be a fairly quick lab, not very much to crystallization, just a couple key concepts you need to know, and a couple simple procedures to do while you crystallize. In an actual in-person organic lab, crystallization takes place at least half of the time while you're doing the labs. It's a pretty common technique. It's quick, it's easy, and it's very important anytime you need to get a solid out of solution. All right, well, first thing is we need to know what a crystal is and what exactly crystallization is. So when we're talking about a crystal, it's any solid materials where your molecules are going to be arranged in a highly ordered structure. The pictures on the top right show you 3 different types of crystalline structures. A pure crystalline structure is going to have a very laminated, fairly symmetric structure. Then you can have a polycrystalline structure, and if you notice from the picture, you have little chunks of normal crystallines instead of just one big chunk. That's the defining point there. And for amorphous crystals, which are like your big, heavier, chunkier crystals that don't have a defined shape or anything, that's just a lot of really small agglomerations of crystals that come together. And anytime you have any crystalline growth from any media, that is crystallization. It's just the process of crystal formation due to crystalline growth. So on the bottom here, we have 3 different pictures of different types of sugar, and these are all just simple crystals that are formed from a sugar molecule. Kind of in the middle right, we have a demonstration of what the sugar molecule kind of looks like. It's, if you haven't seen it before, it's basically a glucose molecule bound to a fructose molecule. And those together it's called sucrose is the actual name for it. So that's their standard table sugar. And you can have a whole bunch of different types of sugar, as you can tell from the pictures, and I'm sure you've interacted with them. And that's just differences in crystallinity, pure crystalline, polycrystalline, amorphous. If you know, like powdered sugar, the crystals are all broken up and the edges are sheared off. That's why it's fluffy and doesn't refract light, whereas pure crystalline sugar can actually refract light and it looks translucent, light goes through it. And then you have like brown sugar, that's just sugar with, honestly, it's contaminants in it that give it a little bit of extra flavor. But they're all simple types of crystals, and they're all the exact same thing, just sugar. All right, when we're talking about crystallinity and forming crystals, one big thing we have to talk about is solubility principles and the effects of polarity and temperature. Now, basically, anytime you do crystallization, the first and most important thing you need to consider is selecting a solvent. This solvent is basically going to dissolve everything you have and make one big homogeneous solution. That's the key. Everything has to be homogeneous in solution to have a crystalline structure at the very end. So not every organic compound can use the same solvent. Some organics can be dissolved in water. Others can be in, like a dichloromethane or some type of ether system. Some require just pure non-polar solvents like a hexane or, just a flat chain carbon. So what determines the type of solvent you need generally is going to be the polarity of the molecule you're working with, or what you want to separate. Now, polarity, if you've forgotten, which I'm sure a lot of you have, is just a measure of the separation of the electric charges over the structure of a molecule. If something's polar, it doesn't mean it's a pure positive or a pure negative. It just means it has an electric dipole moment, meaning at a certain point in time, the electrons in that molecule will be congregated more in one area than they are in the other. And this gives the molecule kind of like a magnetic pole, but it's not a true positive, it's not a true negative, it's just one side of the molecule has more electrons, so it's partially negative, and then the other side, since there's less electrons there, partially positive. So the key takeaway is it's not a true positive or negative. If we're talking about true positive and negative magnetic moments, we're talking about ionic molecules, charge separation, stuff like that. So when something is polar and it has a dipole moment, that can be measured, and that's measured as a value called a dielectric constant. Anyone who's done any engineering or electrical work, all materials, resistors, conductors, capacitors have dielectric constants that determine how well electrons can pass through a media. And it's represented by a little sigma, a little kind of a curly E there on the third point. So the higher the dielectric constant, when you see that value, that means the molecule you're looking at is more polar. So the higher the number, the more polar. That's all you really need to know about that. And here, this yellow bullet point down kind of near the bottom is one of the key important points in chemistry, all just a general, simple common sense thing. And what it boils down to is like dissolves like. If you have something and you take something else that's very similar to it, either in structure or electronic properties, polarity, liquid versus liquid, more often than not, it'll be able to dissolve together. So like dissolves like. And what this means here is for a polar solvent, we'll dissolve polar compounds, and nonpolar compounds are dissolved by nonpolar solvents. Pretty simple, straightforward, common sense stuff. So the last thing you really need to look at in terms of solubility and forming crystals is temperature. Anytime you need something to be soluble in a solution to dissolve, if it doesn't dissolve straight away, you either add heat to it in terms of a temperature increase, or you stir it vigorously. Now, honestly, it's kind of weird to think about, but stirring and adding heat from like a hot plate or a flame or heating it on a burner, it's the exact same thing. All you're doing is you're introducing kinetic energy to a system. Of course, if you're heating it with fire or a heating element, you're adding a lot more. So, things can boil, it goes quicker. But stirring it is the exact same thing. You're adding outside energy to a system. And that extra energy has helped to move things that like each other together, break things apart that can be broken apart, and it's just a simple kinetic energy transfer. But when we're talking about solubility and crystallization, we generally want to use heat because to find a good solvent, you need something to be dissolved at a warm or hot temperature, because one of the key points is to cool it down and force crystals to come out of solution. So generally we want something that at room temperature that your solid might not dissolve fully, but if you add a little bit of heat to it, it will, and that'll help get better crystals and a better yield. All right, we got a couple examples here of some polar, nonpolar, and slightly polar chemicals. The top one, of course, we have water. It's very highly polar. It's got a defined positive and negative part of it. The oxygen, there's more electrons there, so it's going to be the partial negatives there, and the hydrogens, there's going to be less electrons, so that's the partial positive. It's very highly polar, and as you can tell, the dielectric constant there is 80, so it's a higher number, so we expect it to be highly polar. Now, anytime you're using water as a solvent, what you're going to be looking at is highly polar substances, like organic acids, things like acetic acid, formic acid, benzoic, stuff like that. Things that have a definite pull on them and can be dissolved and attracted by water. Also things like carbohydrates, because you've got a lot of hydroxyl groups coming off of them, and generally your salts as well. Any type of organic or non-organic salt is, for the most part, going to be dissolvable in water, because most salts are actually ionic in nature. Their counter ions can be pulled off very easily in water, and you get a positive and a negative pull, which can work with water. So in the middle, we've got something called dichloromethane, which you're going to be hearing a lot about in this semester and the next. It's a very, very common organic solvent. It's slightly polar. It's got a dielectric constant of 9, so nowhere near, almost 10 times less polar than water, but it still has a very slight polarity, and that's due to those two chlorines. So there's going to be a high electro affinity for the chlorines, whereas the two protons, the two hydrogens there, aren't going to have nearly as many electrons around them, so that's where you get the polarity from. Now, dichloromethane is used a lot because anything that's organic that's not highly polar can be dissolved for the most part in dichloromethane, which is going to be any of your most organic compounds and any of your organic compounds that have, functional groups attached to them off the side, stuff like that. Because generally with your functional groups, there's some difference in electron density between where the functional group is and where it attaches. And that's what's going to allow the dichloromethane to act as a solvent and solvate that area. And then at the bottom, we have an example of a nonpolar, very commonly used compound for solvation, which is hexane. And that's just a 6-carbon chain, and it's got a dielectric of 1.9, so almost near zero, so almost hardly any at all. And that small value is brought about by just simple van der Waals forces, London dispersion forces, or temporary dipoles, where just the natural movement of electrons around a molecule will make small instantaneous polarity charge areas. So it's, overall you measure the entire electric structure, there's hardly any difference in the molecule. But just occasionally you might get one tiny little area on the molecule where there's one less electron floating around, so there might be some attraction, but most of the time hexane is completely nonpolar. So what we use hexanes for is to dissolve things like hydrocarbons, oils, waxes, greases, stuff like that. Things that don't have high areas of electron density or don't have any polarity or any ionic structure. And so that's just a general three very common used. As a matter of fact, in these labs, water DCM, that's the acronym for dichloromethane, and hexanes are probably your three most used solvents. Occasionally we might use an ether, but those are very, reactive to oxidation and can cause us fires. So we kind of stay away from those. But that's just a quick example of some polar solvents. All right, and I touched on this a little bit, just briefly, but we'll go over it more in depth here. But crystallization is a very common, probably the most commonly used purification technique. Because when you crystallize something out of a solution, it's naturally going to separate impurities. They're not going to form in those crystals because generally crystals like to have pure substances. Every once in a while you might get a small impurity in it, but even just a small impurity is a lot better than having a large amount, 20% or more, which you're going to have in most of your organic reactions. So first and foremost, crystallization is only used to purify solid compounds. If it's a liquid or a gas at room temperature, not going to do purification, not going to use it. So anytime you do any lab and you see that there's going to be a crystallization step, that should tell you right off the bat in the lab, and of course for quizzes and exams, stuff like that, that your final product you're looking to get is going to be a solid at room temperature, because that's a number one key. So you should be knowing you should be getting a solid at the end. So generally, depending, like we said earlier, depending on the polarity of what you want and what you need to purify, you're going to select a specific solid. Again, water for highly polar, DCM for kind of, hexanes for non, stuff like that. And like I said earlier, we need to select a solvent that has sort of good solubility at room temperature, but basically 100% solubility at high temperature. We want to add that extra heat because the point is to force these crystals out, and to do that we got to drop the heat after we've dissolved everything and let the crystals naturally form out of solution to basically expel the impurities that might be around them. So we want to dissolve it in a hot solvent, but so it has to be soluble in that hot solvent, but it also has to be less soluble in cold solvent. So if something's soluble in hot water, but also soluble in cold water, that water is a horrible solvent because you'll never force crystals out of it. You have to do something different. But if you've got something that, you dump a powder into water and it doesn't dissolve, but you heat it up and it does dissolve, that's a good one because at room temperature it's not soluble, so when it gets colder it's definitely not soluble. So that's kind of the key to figuring out what solvents are. And I will tell you this because this was my concern when I was taking these classes, is you generally, until you get to high-end graduate level, you're not going to know what solvent to use for the most part. For the most part it's a trial and error and just an experimentation thing. You get to know after time what might work, but until you start mixing things, you'll never know. So don't really expect to ever know, oh, this chemical is going to be perfect to solvate this. It's a trial and error thing and a general question. So any questions you're going to be asked are going to be really, really general type stuff. It's not going to be, what solvent will dissolve this? Yeah, that's too much information for y'all. So when you do heat something up, you can heat it up and it's going to be dissolved in the solvent. Both the pure compound you're looking for and any impurities are all going to dissolve when you heat this up in this solvent because you're going to have previously picked the solvent that will work. Now, once it's nice and hot and everything's swirled up and homogeneous and you don't see any solids, you're going to take those crystals and you're going to start to cool them down. Generally, what you do is you put it into an ice bath, and that forces a rapid cool down. Once you start seeing crystals form, then you're going to take something. Generally, what we use is called a Buchner funnel, or Buchner, depending on who pronounces it. And it's just a wide mouth funnel that you put a filter paper over the little holes in the funnel, and it's got a vacuum attachment to it, and you can pull air all across it and suck all the liquid out. So it makes things go a lot faster than just a standard, gravity filtration. Because in gravity filtration, we generally only use that if we're looking to keep the liquid. But since we're doing crystallization, we want to keep the solid. So, gravity filtration can work because you might get some solid as the liquid goes through the filter paper. But gravity filtration is very slow, so you're going to have a lot of the stuff just go through or not crystallize well, and you're changing temperatures. So when you're wanting to crystallize, you're generally going to use vacuum filtration on a Buchner funnel. So you've got your crystals that are formed in the bottom of your flask. You started to notice them. So you're going to basically slowly pour it onto the Buchner funnel that's being vacuum pumped. And as they go in, you kind of pour in the very center and make little concentric circles around it to help the crystals agglomerate in a big area. And you keep pouring the liquid kind of in the same place because you want all those crystals that are in solution that haven't come out. When they see the other crystals, when they hit them, they're more prone to agglomerate and form more crystals. And then the liquid that doesn't have any crystals left will be drawn out of the bottom into that flask on the bottom. And then at the very end, you keep the vacuum going and for another good 2 or 3 minutes, and it draws all the liquid out of the system. And all you have left on your little filter paper in the Buchner funnel is just a pure crystalline solid. And that's just crystallization. Anytime you do crystallization in an organic lab, it's that simple 2 or 3 steps. Heat it up to dissolve it, to get everything dissolved, everything soluble in the solvent. Then you're going to flash cool it down in an ice bath. For the most part, some solutions might need a slower cooling at room temperature, but generally it's an ice bath. Then you're going to filter it once you start seeing crystals, and you collect them, and they should be really pure crystals. That's a pretty simple technique, but it's really powerful in terms of getting a very solid, high yield of your compounds. All right, so let's talk about this week's lab, which is going to be the hot gravity filtration of benzoic acid solution. Basically, if you were in the lab in person, you would have the TA would make you a kind of a mixture of benzoic acid and an unknown contaminant in it. And we would give that to you, and we would tell you to dissolve it, recrystallize it, and just get pure benzoic acid out of it. So this comes up a lot in labs or anytime you're doing any research when you have something and you're pretty sure it's something, but you're not 100% sure. So you can just recrystallize it, get the impurities out of it, and be 100% sure. So what you would do is you need 2 beakers. In your first beaker, you're going to take 50 milliliter beaker, somewhere around there, no more than 100 milliliters. You don't want it too big. It would take too long to heat up. You're going to put about half a gram of your impure benzoic acid compound and 20 milliliters of water. And you're going to put that on a hot plate, and you're going to heat it up until all the solid is dissolved to make a homogeneous solution. Depending on what the contaminant is, for some of y'all, it might have taken longer to dissolve and heat up. So if that's the case, some of your water may evaporated. So occasionally you would add a couple, 2 to 5 extra milliliters of water just to try to maintain that volume around 20 milliliters. The key point is not to let it dry out, because if all the water evaporates, then it just drops back down, and any of the contaminants and everything are still combined with the benzoic acid. So we don't want that to happen. So don't let it get too hot, don't let it dry out, and don't get it below 10 milliliters, because then we start getting issues with, superheated water and too many things to worry about. So when you do this in person, the heating needs to be controlled. You don't crank it up, just slowly raise it. And any questions, of course, always ask the TA if something's like that going on. But so that's your first beaker. You got that heating. And another beaker, another 100 milliliters or so. You want another 25 milliliters of water, and keep that hot, just like a light boil, roiling boil. Just not boiling and spewing water everywhere, but just very lightly boiling. And what this is going to be used for is before and after any of the filtration that we do, use it for rinses and to get any excess crystals out of the bottom of the beakers. You can dissolve it and swirl it around in the hot water, and then let that cool down to room temperature again, and pour that in there and get as many of your crystals out as possible. So you set up a gravity filtration system, and what you're going to do is you're going to use say a 150 milliliter Erlenmeyer flask, which is one of the conical flasks. Now, a beaker is the wide mouth cylindrical flask. Erlenmeyer is conical, and it comes up to almost a point with a very small opening. and it's used generally for collection. That's what we use them most for. So what you're going to do is you're going to put a funnel filter on top of it, and you're going to take filter paper, put that inside the filter, and you're going to soak it with some of that hot water to make it adhere to the edges of the glass filter, and so there's no area where your compound can leak out the sides, stuff like that. And also, one of the key points is for this, we're filtering it to get any basically insoluble impurities out of it first, because we just want the dissolved substance. And if there's like sand or just any contaminants from something, we want to get that out first, because sand won't dissolve in water, so that's what we were looking for. So we want to use that little hot water on the filter paper, because when you pour your dissolved solution in there, if it's too cold, it'll instantly crystallize and gum up the system. So we want the neck of the funnel and that filter paper to be hot, so it won't get instantly crystallized when it hits that. That's one of the key points. So, and what you're going to do is once the funnel is hot and the filter paper is fully wetted and all your stuff, everything is dissolved that can be dissolved, you're going to pour that beaker 1 through the gravity filtration, and you do as quickly as you can. And if any crystals show or anything starts to block it, you pour some more of that hot water that was in beaker 2 in there to help dissolve it and get it through. But this first step, gravity filtration, anytime you do gravity filtration, you always want to keep the liquid. And anytime you do what we talked about before, the vacuum filtration, you keep the solid. So anytime you see gravity filtration, you're keeping the liquid. So the liquid that's going to go through is going to be your dissolved benzoic acid plus any dissolved impurities. And inside of the filter paper is just going to be anything that's not soluble, that's going to be pulled out of solution as it goes through that filter paper. Okay, after we've done the gravity filtration to remove any insoluble impurities, you're going to have just your flask of your fully dissolved benzoic acid solution with any dissolvable impurities sitting there. And the key thing to think of is we still have to keep it heated just to keep everything nice and dissolved. But one of the key points of crystallization is your solution has to be not too dilute. It has to have a pretty good concentration of your compound in there. If it's too dilute, crystals don't like to form. They don't bump into each other often enough. So for this particular lab, we don't want basically any more than 25 milliliters of liquid in there, because you're rinsing with the water and you're pouring some extra hot water in there to keep things hot, so you might have some extra water in there. So if you have more than 25 milliliters, basically you're just going to keep heating it on that heating mantle until it evaporates some of the water out and gets around 25 milliliters. And once it's there, you're good. So once you have around 25 milliliters or a little bit less, that's fine. 25 in that range is a good number. You want to just keep heating the plate until the volume's down to what you're looking for. And once you're to reach that desired volume, you're going to take the flask off of the heating element, of course, turn the element off. And then for this specific one, we're just going to let it cool on the bench top. We're not going to use an ice bath or anything, because we don't want any thermal shock or anything weird. We're just going to slowly watch it so you can watch the process. When you're going quick in other labs, it's generally okay to use an ice bath. But for this specific, I can't talk today. For this specific lab, you want to just let it cool on the bench top. Luckily, benzoic acid can drop out of solution pretty easily, so it won't take very long to cool it down. So what you're going to do is you're just going to let it cool down to room temperature, and you will, for this experiment, you'll start seeing crystals form. If in another experiment you don't see crystals, even if it's cooled down to room temperature, then basically you would use an ice bath at that point. But for this one, it's going to, because we've done this so many times, and benzoic acids crystallization temperature is pretty known, so it's a pretty simple reaction. Well, not even a reaction, it's just a physical property. So that's one thing to think about in your other labs. If you don't see crystals, the reason generally is it's not cold enough, so the first thing you do is put it in an ice bath. Then another reason you might not get crystals is because there might not be enough nucleation sites, and that's talking about what I said earlier, where your solution can't be too dilute. If it's too dilute, those crystals won't bump into each other, or there's not enough little tiny impurities in there for crystals to form around and form their own crystal seed. So a good thing to do then is to take a glass rod, a long glass rod, and gently scratch the inner surface of your flask on the sides and the bottom. And what that actually does is it kind of etches the glass, and it makes tiny little imperfections in the glass surface where crystals can adhere to and start forming nucleation sites. Generally, if something's going to crystallize and it doesn't do it normally at room temperature or an ice bath, as soon as you start scratching it with that glass rod, crystals will start to form. It's a pretty quick process. So it's all about patience and trial and error and seeing what it does. So sometimes it's slow, and sometimes you might have to do 3 or 4 steps. But if you have done everything right, you will get crystals at some point. It's just you might need a couple extra techniques here or there. Okay, so hopefully in this case, if you were in the lab, you've got a nice flask cooled to room temperature with plenty of crystals formed in it, which basically happens to everyone with his lab. It's really simple. It's made to work every time. So you would set up a vacuum filtration system here, just like it's shown. You need a ring stand and a ring clamp, and you need to clamp it around this specific filter flask. And the reason is you're going to be pulling a vacuum on this, so there's going to be extra force applied to it. And that Buchner funnel on top is a ceramic funnel, and it's about twice as heavy as the flask, so it's really top-heavy system. So if you don't have it clamped, and you start pulling that vacuum, it's going to tip over, flask is going to break, chemical everywhere, so we don't want that. So anytime you're doing any vacuum filtration, always clamp your filter flask, 100% all the time. All right, once you have that set up, you put the Buchner funnel on top of it. There'll be these little rubber stoppers that you put in to help form a seal against the side of the glass. And then you connect a vacuum tube to the side of the filter flask and to the vacuum inside of your fume hood. It's labeled. See, the vacuum is going to be yellow on your fume hoods. So pretty simple. And once you have that going, you're going to take filter paper and make sure you choose a paper that just covers the holes. You don't want any extra paper bunched up on the sides, because that's areas where stuff can congregate and not dissolve well, not get through. So you want the filter paper just to be basically just a tiny bit smaller than the inside circumference of that Buchner funnel. You might have to cut it and mess around with it, but that's what you're going to do. So once that's in there, before you turn anything on or start filtering anything, just use a little bit of that warm water to soak that filter paper to make sure it's adhered, because you don't want to have it poking up in anywhere so liquids can get under it. And once that's firmly stuck on the funnel, you turn the vacuum on, and you'll instantly know that the paper will sink down. You can hear it. Everything will be nice and tight on there. And once that vacuum is going, then you're going to take your flask with your dissolved benzoic acid that's just starting to form crystals, and you're slowly going to dump your crystals and what's called the mother liquor. It's an old term. It's basically the filtrate. It's anything that your crystals are coming from. It's basically anytime you see mother liquor, it's the solution your crystals come from. And you're going to pour that into the funnel. And the best way to do that, I found, is basically try to dump it in the dead center. And then when crystals start to form a pile, you just kind of little concentric rings of your liquid around that, and it'll form just a really big nucleation site where a lot of the crystals will congregate. Otherwise, you'll get crystals all over the side of the funnel, and some might splash out. So you need to do it quickly, but not haphazardly. You need to be careful while you're pouring it, that type of thing. And then once everything's out of your flask, you can have a lot of crystals adhered in the flask. You can take a little bit of that hot water you had left in the second beaker, pour it back into your flask, swirl it around, get those crystals dissolved up again, let it cool down, do the same thing, dump it in there, and try to get out as many crystals as you can. And you're just going to do that until everything's out to the best of your ability. And then you're going to keep that vacuum on for an additional 5 minutes to let it pull any excess liquid out of it and let your crystals dry as much as possible. And now, hopefully, after everyone has a nice batch of crystals on their filter paper and they're fully dried, you're going to carefully take that filter paper out with the crystals on it, and you're going to take it into the scale room, and you're going to weigh it. And you're going to see the weight of these purified crystals you have, and you're going to compare it to your initial 1/2 gram weight. It's definitely going to be less than 1/2 gram, because there's going to be impurities in there, both insoluble and soluble, that aren't going to be in those final crystals. So you might have, as little as 1/4 gram after purification. It just depends on whatever the TA would make up for you. So the important thing about benzoic acid specifically is it's very flaky, and they're big, fat, flat, flaky crystals. So any gust of air or wind can make them just basically fly off. So you got to be really careful. The best thing to do is get one of those slightly concave watch glasses and kind of put it over it. It's kind of like a lid, and just to be careful on your way back to the scale room. So once you have the weight of your final product, we need a percent recovery, same thing as a percent, yield of any reaction, and that's just going to be the final weight of the crystals that you got divided by that half of a gram of initial contaminated crystals times 100, and that's your percent recovery. For this, generally, anytime you're doing crystallization, of course you want the highest, but depending on the percentage of impurities you have, it might be low. You never know. You can't control it like you can like a reaction. If you do a reaction nice and slow and everything correctly and do what you're supposed to, you get a higher percent yield. But when you're purifying, you never know what your percent recovery is. It's just you get what you get. But this is something, anytime you do any type of crystallization, this is something you're going to be doing. A percent yield, percent recovery, they're all done the same way. It's whatever you've got divided by whatever you had times 100. And that's the percentage of either recovery or percent yield. All right, that is honestly the end of the lab. Nice, quick, and easy. So, of course, the important part at the end is always clean up and proper disposal of chemicals, waste, stuff like that. So any waste you have from this specific lab really is going to go in two places. Your filter papers, you're going to have two of them, one for your initial gravity filtration and then one for your vacuum filtration. Both of those filter papers and any of the benzoic acid you purified, it's just going to go into waste. It's super cheap. You don't need to worry about it. You wouldn't have kept it for anything later on. But solid waste, of course, if you forgot, is the big black bin in the waste area of fume hood. So those go in there. Of course, anything you broke would be going into broken glass and cleaning that up as you go along. Any of the liquid waste, which including the filtrate and anything left in the flask, stuff like that, that all goes in the aqueous waste container for this lab because it's all water-based. Everything's dissolved in water. We didn't use anything liquid other than water. And then, of course, you would have to clean up your fume hood, wipe it down, make sure it's all nice and well before you could leave, as well as the balance room. Since that's being used, everything has to be cleaned and properly put back there. So once all of that would be done, your TA would sign you out. So hope you like this quick and simple online, not doing anything lab. It's a really powerful technique for purification. So remember that anytime you see crystallization, it's always going to be used for purification of your final, generally of your final product. You might have some multi-steps, like something called a convergent synthesis, where you do a bunch of steps and they come together at the end. So you might have a bunch of purifications by crystallization, but at the end you would do one final one. So the key points there are crystallization is purification. Crystallization is based on using a solvent and the polarity differences between the solvent and your impurities and pure products you're looking for. The key point in the solvent is it's kind of trial and error what you need, but everything needs to be dissolvable in a hot solvent, but needs to be a whole lot less soluble when it's cold to let crystals form. And you can let crystals form by letting it cool naturally to room temperature, or you can use an ice bath to do it quicker, or if all else fails, you can use a glass rod to kind of scrape the edges of the flask to form nucleation sites. And that's about it. So I hope you have a great week, and we'll see you again next week for our fourth lab.